Okay, so today we're going to take a look at some calculus being applied to what's called RC circuits. R are for resistors, and C are for capacitors. Now, in class we've talked a little bit about solving some of the intricacies of RC circuits, but we haven't, at least depending on when you're watching this, we haven't yet talked about the calculus side of it. If you're watching it later and we have talked about the calculus side of it, then this is going to kind of give you a refresher on it so that you can see it outside of class. If you haven't seen it yet, that's okay, but keep in mind that I'm going to operate under the assumption for this video that you're familiar with solving for some of the values of capacitors, either at time equals 0 or at time goes to infinity. We've done a little bit with applying loop rule and junction rule and Ohm's law on these, and I'm going to be using those in the calculus side of this. So if you're not familiar with those, a bunch of what I do is probably going to be Greek for you. We need to know those relationships. Ohm's law, it applies to resistors, and it has delta V equals IR, or, as we've talked about in class, sometimes we represent the potential difference as squiggly E, which is the electromotive force. This usually references the battery, but it's another way of writing it. It's also kind of common because they like to do that on AP exams. Capacitors. One of the things we need for capacitors, and I've talked about this before, Q equals delta V times C, where Q is the charge on the capacitor, delta V is the potential difference, or voltage across the capacitor, and C is the capacitance. Now, there are a couple different ways that we can write this. This can also be written as delta V is equal to Q divided by C, where Q is the charge on the capacitor, C is the capacitance, and delta V is the potential difference across it. As you may have seen from some of the videos, a lot of these equations we're going to have to work with quite a bit. We change it from this form into this form. Be familiar with one of them and how you're going to work with it. All right, let's take a look at what happens to a circuit using calculus. What I'd really like is the following. Let's look at a circuit like this. We've got a capacitor here, a resistor here, and a battery over here. We're going to have a battery with a potential difference across it of squiggly E. We've got a capacitor that has a capacitance of C and a resistor that has a resistance of R. Now, these could be any sorts of real-world numbers. This could be 6 volts, this could be 10 microfarad, and this could be 100 ohms. Could be anything. We're going to use variables so that we can actually plug anything in and see what our end results are. All right. What I'd like to know is this. We're going to start off and say that the initial charge on the capacitor, I'm going to put it like this. We're going to say that it is discharged, and that Q, lowercase q, of 0 is equal to 0 coulomb. There's a lot of C's. Sorry. C in this case is for coulomb, and then C in this case is for the capacitance. That being said, what I'm trying to say is there's no charge on the capacitor at time equals 0. Now, we've talked about this in class. The battery is going to let positive charges out from the positive side of the battery, and they're going to collect on this side of the capacitor plate. As a charge comes in here, a positive charge, it will push an identical positive charge out over here. So even though we're collecting charge on this plate, the same amount of charge gets pushed out the opposite side over towards the battery, and we end up with junction rule still applying. We have the same current through these. The problem is, as charges start building up on this positive plate, they start pushing back against the battery. This is why, as I mentioned before, the capacitance is a function for how much charge it can have of the potential across it. If you have a bigger potential difference on your battery, it's going to push harder, and it will push more positive charges onto the capacitor plate until the capacitor gets too full and pushes hard enough back that everything stops. All right. So that's a little bit of information there. Here's what we're going to do. What I really want to know is this. I want to find Q as a function of time. I want to know the charge on this capacitor as a function of time. I'm going to call this simply lowercase q. And here's another thing that I'm going to set up. There are a few things that we probably want to define initially. When time goes to infinity, the capacitor is going to drive all of the current to a stop. It's going to block all current coming out of the battery, and there'll be no current going through this side, and the circuit will be effectively not actually having a current through it. If I apply loop rule tells me that if I take the potentials, I'm going to go across the battery, it gives me squiggly E. I go across the capacitor, and the capacitor is taking energy right now to store it. So we're going to say delta VC. I go across the resistor, delta VR, and then I end up back where I started. That's going to be equal to 0. At time equals infinity, let me fill this in a little bit more. E minus the potential difference across the capacitor, here's where this comes in handy, is going to be the charge across the capacitor divided by the capacitance. At time equals infinity, the capacitor will be completely charged. I'm going to call that Q naught, where Q naught is equal to total charge. Maybe I should call that Q1. Naught is usually used for the beginning situation, and we're actually talking about the end. So we'll go ahead and call it Q1. It doesn't really matter what you call it, but that's okay. We're going to have the potential difference divided by the capacitance. Oops. The potential difference is the charge divided by the capacitance, minus delta V of the resistor, which is going to be equal to I, the current, times the resistance. Now at time equals infinity, as time goes to infinity, our current will actually go to 0. And if this is 0, then I get the following. At time equals infinity, or time goes to infinity, the potential across the battery will be equal to the final charge on the capacitor divided by the capacitance. I'm going to set something up here. I'm going to switch this around where Q1 now represents the potential of the battery times the capacitance. I am not given the total charge of the capacitor. I am, however, given the potential difference of the battery and the capacitance, so I'm going to make a term for now that is made up of those two. But if I have to switch this out in the end, technically I wouldn't want the total charge as part of my answer, although I'm probably going to leave it that way for this, but we'll know how to replace it out there at the very end. That's a small side step, but it's going to clean up some of the stuff that I do. It doesn't actually matter. This is a constant, and these are both constants, so I'm just replacing one thing with another. Although it will make this a little bit easier on the eye and easier to understand when we get to the end of this problem and want to double check our answer. Now let's move away from time equals infinity. Here's what I'm going to do. I'm going to set this up again. We still have loop rule. And what I wrote out actually applies at all points. Doesn't matter if it's t equals infinity or not. I go across the battery, I gain squiggly E. I go across the capacitor, and I lose whatever the potential difference is across the capacitor, and then I go across the resistor and lose its potential difference. So I gain squiggly E minus the potential difference across the capacitor. I'm going to call that Q divided by the capacitance, where Q is equal to the charge at some time t, minus the current times the resistance. This is the potential difference across the resistor, and that must come up to 0 by loop rule. I'll give you a hint. Whenever you're doing calculus of circuits, you set up your differential equation by applying loop rule. This rapidly becomes a differential equation by bringing in something that I've mentioned before. The current is equal to dq dt. It's the rate of change of the charge with respect to the time. If you're asked for a differential equation to set one up on the AP exam, basically after you get to this point, this is a differential equation. You can leave that and move on. If they only ask, and they'll sometimes do this, if they say, write but do not solve the differential equation, set up loop rule, do these replacements, and once you get here where you have constant, 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 Q, Q, and T, so we're going to be integrating with respect to Q, the charge and time. These are variables, and everything else is a constant. You're done. This is a differential equation. If, however, they ask you to write and then solve, we're not actually done. And we're not done with this problem yet because I'm going to show you how to solve this. But this is the differential equation. I've got a bunch of constants and the things that I'm looking at, the charge on the capacitor as a function of time. Here's what I'm going to do. I'm going to replace this squiggly e with the thing that I defined earlier. You don't have to do this, but I do recommend it. And so if squiggly e is equal to my total charge divided by the capacitance, then I can actually replace that. So I'm going to end up with this. Total charge, Q1, divided by my capacitance, minus, that's this thing, minus the charge on the capacitor at some time t, whatever point I'm looking at, divided by c, minus dq dt times r equals 0. I'm going to do a little bit of math here for us to keep us moving, but this is more or less my differential equation. This would probably not be the solution you're looking for on the AP exam because you are not given Q1, you are given squiggly e. I think that's, I'm not certain if it's an epsilon or a sigma. I never actually remember, so I'm going to call it squiggly e continually. You can laugh all you want. All right, here's what I'm going to do. I'm going to get the following. 1 over c times Q1, my total charge, minus whatever charge happens to be on the capacitor at a given time t, minus, I'm going to add this over to the other side, and we end up with dq dt times r. I'm going to do a little bit more math. So I added this over and I put these together. I'm going to do a little bit more math because what I need are all the constants and time, if I can, on one side, and then I need dq and everything related to q, all the variable, on the other. I'm going to set this up. I'll get the following. I'm going to divide both sides by r and multiply both sides by dt, but I'm going to end up with the following. dt rc divided by RC, I should say, is equal to dq over q1, my total charge, minus q. This is my variable, dq and q. And this is a constant, the total charge on the capacitor at the end of time. So this is how much charge can total end up on there. This is how much we happen to have at some time t, whatever we happen to be looking at. All right. Now that I've got this, I've just moved a few things around, that's fine. I can do the following. Here's where we're going to integrate both sides. I have a little small piece of time and I have a little small piece of charge, and what I want to do is I want to get Q as a function of t, which I'm going to call just little q. That's why I've been avoiding using little q. But here's what we're going to find out. So I'm going to integrate this side. Well, these are constants, so I end up with 1 over RC integral of dt. I'm going to integrate, well, and find the time. Over here, I'm going to integrate the charge from 0 to little q. Little q is going to be my function. It's basically q at some time t, which is what I've got listed here. Now this represents one specific time, which I don't actually know because I haven't filled that in, but what I'm integrating for here is whatever the charge is going to be on the capacitor after a time t. So I'm actually going to integrate this from 0 to t. Now technically this is bad form because you should never have as a limit of integration a variable that you're actually integrating. Forgive me, math teachers, I'm going to do something a little off. dq over q1 minus q. Where this is the charge, this will be the charge at some time t. All right. Well, this integrates pretty easily. I have t over rc minus 0 over rc, which is just 0. Here's where we're going to need to do a little bit more work. Not a whole lot, but a little bit more work. q1 minus q. Technically, I've got this constant in here. It's causing a little bit of problem. So here's what I'm going to do. I'm going to define some function u as the total charge minus my actual variable, Q. This means that if I take du, remember this is a constant, so it becomes 0 minus dq. A little bit of u substitution here. This tells me that du is equal to negative dq. So what I can do is the following. I end up with t divided by rc equals negative integral of du. I have a negative that shows up from the du, and then over u. Now I'm going to be lazy here. I'm not going to change my limits of integration. They were from 0 to q. They're going to be something different for u. In fact, I think they'll actually still be 0 to q, now that I think about it, because they won't be changed by that function. But before I evaluate the function, I'm going to do the integral, and then I'm going to put it back into the function that it was. So my limits of integration, even if they are not 0 to q now, when I put them back into this, they will return to 0 to q back over here. I've got the negative here, so I'm going to end up with, let's see, negative t over rc. I'm going to do something tricky and move that over to the other side. And I'm going to find that this is going to be equal to, well, the integral of du over u, or dx over x, is the natural log of u, evaluated from 0 to q in this case, I think. But definitely, here's what I'm going to do. Natural log of switching u back to what it was, evaluated from 0 to q. Here's why I say I think these are the same limits of integration, but even if they're not, before I actually evaluate them, when I switch it back to this, they do return to 0 to q. So even if they were something different here, they would switch back to this when I evaluate it. We end up with the following. Negative t over rc equals the natural log of q1 minus q, evaluated from 0 to little q, where little q is actually what I'm looking for. It's the charge as a function of time. All right, so I'm going to end up with negative t over rc equals natural log of, let's see, I'm going to have, okay, so natural log of q1 minus 0, let's see, and then minus the natural log of q1 minus little q. Oh, I've got that reversed. I apologize. It's been a long day. My upper limit of integration is little q. My lower limit of integration is 0. I've been thinking about doing this with the non-limit of integration approach, which we will take a look at when we get a chance. All right, so this can also be written as negative t over rc equals the natural log of, and here's where we're going to incorporate some rules of natural logs. q1 minus little q over, sorry, that should be q1. This is minus 0, so it's just natural log of q1, my total charge. That's just a constant. But when you have natural log of one thing minus natural log of another, with the rules of natural log, you can actually put that as natural log of the first thing divided by the second. Here is where we're going to take the next step. E raised to both sides. I'm going to get rid of that natural log, and I get the following. E raised to the negative t over rc equals, the e and the natural log cancel each other out, and we are left with q1, our total charge, minus q, which is a function of time, divided by q1. I'm going to finish this up, multiply both sides by q1, then add this over and subtract the other one over. We're going to, too many clicks. We're going to end up with the following. Finishing this up, feel free to pause this and double check the math, but I'm going to end up with a positive q of t. This is my charge on the capacitor as a function of time, and it should be equal to q1, my total charge on the capacitor, minus q1, the total charge on the capacitor, times e, the exponential, raised to the negative t divided by rc. Another way of writing this, in the more compact way, is the charge on the capacitor is going to be equal to our total charge that can fit on the capacitor, charge as a function of time, times 1 minus e raised to the negative t over rc. Finally, if you want to put it in terms of what has been given to you, Q1 is equal to, oh dear Lord, where did I put it? Q1 is equal to squiggly E times C, so I can finish this up. This is a really long slide, sorry about that, but that's how it goes. Squiggly E times C times 1 minus E raised to the negative T over RC. Here is your completed, actual completed evaluation. The charge as a function of time is this. Let's step back from this one and see why I like using QT. Let's double check our answer. At time equals 0, how much charge did I have on my capacitor? Well, at time equals 0, we said that the charge was 0 because it was discharged. If I put t equals 0 in here, I have e raised to the negative 0, so that's 1. 1 minus 1 is 0 times q total, doesn't matter. I do actually end up with a charge of 0. This meets my initial boundary condition. What about as t goes to infinity? T goes to infinity. Well, this becomes infinitely big, divided by a constant, doesn't matter. We have e raised to the negative infinity. Well, e raised to the negative infinity, or more accurately, the limit as e goes to the negative infinity, or e raised to the negative limit as x goes to infinity, we actually find that this whole term becomes 0 because we actually end up with it being divided by an increasingly large number. So 1 over an increasingly large number ends up eventually, as that number goes to infinity, goes to 0. So we have 1 minus 0, that disappears, and we have 1 times, this is why I switched it out, the total charge at t goes to infinity, the charge on the capacitor goes to Q1, the total charge. This equation meets our boundary conditions. And it can be seen best when you treat this as the total charge. Here's our end answer. Here is the charge as a function of time. We end up with an exponential. So we would have 1 minus e raised to the negative t over RC. The final thing that I will say, I'll see if I can make a supplemental video with this, but we're going to talk about it in class. RC becomes an important value. We call it the time constant. RC is the resistance of the resistor times the capacitance of the capacitor. If you have a complex circuit with more than one capacitor and more than one resistor, find the equivalent capacitances and resistances to find the values for the total circuit. All right, this is the calculus of an RC circuit. This is charging the RC circuit. I'll see if I can do one pretty quickly for discharging an RC circuit.